In this short video, I'm going to provide a proof for our law of sines. Recall the law of sines can be summarized in terms of our ratio. Sine of capital A over little a equals sine of capital B over little b equals sine of capital C over little c. In particular, what this says is for any given angle, you take the sine of it divided by the length of the opposite side that's constant for any angle in the triangle. Now, to prove this, we're going to look at two cases. One, the acute triangle case, and two, for an obtuse triangle, just so that it's clear that it applies in both circumstances. So to do this, we're going to just pick any two angles, and it doesn't matter because we could reorient this triangle in any way. So let's just pick two angles that we're going to show that the law of sines holds for. In particular, let's say we've got a triangle labeled in this way here, and we'll look at this angle right here, C. Now, the triangle that you get by dropping a side straight down from the highest point to the side, B, turns out to be a right triangle, because if you drop it straight down, you get a right angle here. And according to the right triangle definitions, or the relationship of the sines to right triangles, or the trigonometric functions to right triangles, you know that sine of capital C would be opposite, which happens to be this length h, over the hypotenuse of that triangle, which would be side A. And if I move the A to the other side by multiplying it across, I end up with the following statement: h equals A times sine of capital C. If I did the same thing for angle A, I would see that the sine of capital A would be opposite, which is h, so opposite. So again, I'm looking at this triangle right here now. Triangle with length, or hypotenuse C, okay, this length down here, and a height of h. Opposite over hypotenuse gives me h over little c. So if I move that c to the other side, I have h is also c sine of A. And since both of these are equal to h, they're equal to each other. So you can then say that A times the sine of angle C is equal to C times the sine of angle A. And if I divide both sides by AC, little a, little c, then you end up with sine of capital C over little c equals sine of capital A over little a, which is the law of sines. And since it doesn't matter which angles I labeled A, B, and C, I could reorient this triangle, that is, flip it around and do the same process. This would work for any two angles, then we could follow the same procedure. And just as an indication that it doesn't have to be the case that h lies inside the triangle, consider the case of the obtuse triangle. From this triangle, which is the triangle ABC here, what I'd like us to do is look at, as we did before, the sine of C. And since I dropped this side straight down, it's still going to be opposite over hypotenuse, which would be h over little a, which, as before, is the same as, by moving the a to the other side, saying h is equal to A sine of capital C. Now, what we want to do is we want to look at this angle A right here. But the problem is the next triangle is now this triangle outside of here. So we got to look at this angle instead of A. This angle right here would be 180 minus A, because the full straight line that is parallel to B would be 180 degrees. But then if we do A is this angle here, then this angle inside the triangle is going to be 180 minus A. So, doing that, we take sine of 180 minus A equals h over the length C. Okay, which means h is the same thing as sine of 180 minus A times C. But here's the trick. Note, for any angle, sine of 180 minus an angle is the same as the sine of that angle. Okay? Now that's easily proved by the difference formula. And I think we've actually proved that in a previous lecture. So if that's the case, then this now says h is equal to c sine of a, which means a sine of c from here is equal to c sine of a from here, and thus sine of c over little c equals sine of a over little a. And all we did was divide both sides by AC like we did on the first case. Proved. And all of it has to do, in this case, the obtuse one case comes from this property right here. Done. We've proved the law of sines.